What do you? Ah, it's so bright. Yeah, give me dark theme. Whew. Much better. Where's I? Yes. What do you think of this sequence? Are we simply attaching 13 to 563? Well, there's nothing to do with that. Also, it's not on the OEIS, so don't bother checking there. Let me show you the next two numbers. And, as the title of this video suggests, square them all. Well, 13 squared is 169. 563 squared is 316,969. Wait a second. Something seems peculiar.
You know that some Redditor will try and make a vid about 6969696. Don't.
Well, too bad. I don't identify myself as a Redditor, but you're still getting one-upped. Okay, back to the problem at hand. My MegaFav number, which is 73,496,969,437, when squared, gives this. Besides the nice square, it is also a palindrome, so it's the same number read either forwards or backwards. Moreover, it's also a prime, making it a palindromic prime. This kind of prime is quite rare. The sum of the reciprocals of all the normal primes diverges. There's a pretty proof of this by Erdős on Wikipedia. However, the sum of the reciprocals of all palindromic primes converges to some constant. So we can call the set of primes a large set, because that sum diverges. And we call the set of palindromic primes a small set, because that sum converges. Usually, we differentiate the size of sets of positive integers by its density in all the natural numbers. But this time, both sets have density 0, which is a consequence of the prime number theorem. There's some weird flickering there, but don't mind that. Here's a simple property of the palindromic primes. They cannot have an even number of digits except 11. That is because all palindromes with an even number of digits is divisible by 11. Let's take our number for example. It has an odd number of digits. If we insert a 9 in the middle so it stays a palindrome and has an even number of digits, and we group every second digit, we see that the white digits and the blue digits are the same digits, just reversed. We know that if the difference of the sum of each group of digits is divisible by 11, so is the original number. Now those two groups have the same digits, so they have a difference of 0, which is also divisible by 11. Therefore, our palindrome is also divisible by 11. Now, onto a completely different type of primes, amicable, which is the word Sprime spelled backwards. We call a number an amicable if it is a prime, and its reversal is another prime. For example, where have we seen some primes before? Oh yes, the sequence in the beginning. 13 is the first number, which is prime. Its reversal is 31, which is also prime, so both 13 and 31 are amicable. 563 is the second number, which is also a prime. However, if its reversal is 365, which is not a prime, so 563 is not an amicable. Our number is not an amicable since we don't allow palindromes to be one. However, we can flip our number in different bases to get different results. For example, in base 4, 73,496,969,437 becomes this number, which flips to that number in base 4. This final step is not required, but for our base 10 brains, 127,790,000,000 and 9,617 is much easier to understand than that mess. We also see that this new number is prime, so our number is an amicable in base 4. In fact, it's an amicable in all these bases under 100. Yes, even 100. This is easier to see. Just split the digits into groups of 2 and rearrange. 379,496,963,407 is also prime, making our number an amicable in base 100. Our number is also a Pythagorean prime, which has a remainder of 1 when divided by 4. By Fermat's two-square theorem, it can be expressed as the sum of two squares. But so many primes have this property, I didn't even bother to animate this part. Now to the more important part of this video, how I found this number. Here, Google Books, why don't you have dark mode? Well, in David Wells' The Penguin Dictionary of Curious and Interesting Numbers, he says if a square ends in the pattern xy, 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 xy must be 21, 29, 61, 69, or 84. He also says that the smallest example is this one, but he is wrong. It's actually this number. Speaking of errors in math books, Matt Parker, if you're watching this, huge fan of your book, and also you. The whole book is funny until right before the end, where it got a little underwhelming. Woo, tangent. Before I talk about how you can program your own squares, here are a few honorable mentions, which are all palindromes. This number looks suspiciously like our MegaFav number, but unfortunately, it's a semi-prime, which is a product of two primes. However, its square has many 69s. Nice. The next number is a palindromic prime. However, its square ends in 3 21s, making it way less impressive. The last one, in my opinion, came at a close second. You can call it a sphenic number, a product of 3 distinct primes. But the impressive thing is how easy it is to remember. It gives a decent number of 69s. The first 3 digits is the number of days in a common year, and this second group of digits is the number of degrees in a full rotation of tau radians. There is no sign of 69 in the square root, and so it can take people by surprise. Here is the most important part of this video. You will need a favorite number. And a square, there is an odd number concatenated with real number. If there is one, you can generate an infinite sequence such as this. The odd number part is required. For example, many squares end in 0, 1, but no squares end in 0, 1, 0, 1. Here is a short proof. All odd squares are in the form 4n squared plus 4n plus 1, and we see that n times n plus 1 is always even. So all odd squares have a remainder of 1 when divided by 8. Consider our number, which is 10,000x plus 101. 10,000 is divisible by 8, but 101 has a remainder of 5 when divided by 8, so this number cannot be a square. Now, before you go and find yourself that square you need, here's a faster way to do it, Wolfram Alpha. Go to wolframalpha.com and type in x squared equals 1, and then your number, finally mod 2 times 10 to the power of the number of digits in your number. If no integer solutions exist, then you're out of luck. However, if you change it slightly, you might get a solution. If there is indeed one, then type in multiple instances of your number. Mod 10 to the power the number of digits times how many instances your number there is. There will be a lot of solutions, and all these solutions Wolfram Alpha gives you, when squared, has our desired result. You might ask, can you generalize this? For example, to other powers. Well, if both your power and your number end in 1, 3, 7, or 9, there's always a unique solution, but I won't have time to talk about this result in group theory. How about other bases? Perhaps. It may be fun to try them out. Let me check that common thread again. Okay, I've changed my mind. My new MegaFav number is 5 million.